for whatever happens that you need to show us. Anyone have any pets for me?
Hi.
Hey, Laura. What else?
I've shown so many pets, but this is my last pet. This is Athena. She's my cat.
Athena. She looks like a little cat.
She is really small. Here, I'm bringing the computer to her because she doesn't like coming to it. But yeah,
And
that's
she's like,
her.
no thanks.
Yeah,
she's very pretty.
She is really pretty. She is a twin brother who's ginormous, and that's Zeus, who I showed last time.
So it's Athena, Zeus, and then Roxy.
Yes.
So does Roxy also have a Greek name? Is she short for a Greek god or Roman god?
No, I named her Roxy when I was 5 because she looks like she had rocks on her back. So.
That's totally 5-year-old appropriate.
Yeah.
Awesome. Thank you for showing us, Athena. She's very pretty.
Thank you.
Caden, I think I see.
This is June.
What?
She's a poodle. She's very much
See,
asleep.
can you turn on a light in your room?
Yeah.
Or that's probably a really mean thing because you just said she's asleep. Sorry, it's really self-centered. Oh, I see a tail wagging. Oh my goodness. There she is, or he is. I'm sorry, I missed it. Which one?
No, yeah. That's
June. What a happy little dog. She seems very happy to see you.
She is.
Super cute. I love that fur. Thank you for sharing. Peter, who do we have here?
Yes, this is Chocolate.
Chocolate. That's
yeah,
appropriate.
I call her Kitty most of the time, though.
Kitty. Aw. Thank you so much, Peter. That's a precious little pet. And
yeah, it
looks like pretty eyes, too.
Uh-huh. Oh, she wants to leave.
What does she think about this? Is she into a lot of people or not so much?
A little bit.
Yeah. She looks definitely like
a pet her all day.
Yeah, I can definitely see that. Awesome. Thank you so much. Very pretty cat. And then Alex, we have a puppy.
Yes, this is Lucky. He's only paying attention because I have a treat in my hand.
Good call.
I might have just woken him up, but that's okay.
Oh, Lucky does look a little bit sleepy, but Lucky is very pretty. Oh, and he got the treat. Good day for Lucky.
He'll go back to sleep now.
That's fair. If only all of us could just do that, right? Wake up for a snack and then go immediately to sleep. Living the dream. Awesome. Thank you so much, Alex. And Jasmine, what overturned dog do you have here? Oops, let me take you off mute. Hold on one second. You got your hands full.
All right, this is my third and final dog.
Third and final dog. Who is lounging.
His name is Loki.
Loki.
He was my stepbrother's dog, and then he gave him to me.
Nice. Oh, hello, Loki.
So he's a very sleepy little guy.
I see that. I like how at ease he is with you. He's clearly your number one fan.
Yeah, we're just straight chilling.
Both of you live in the dream. Awesome. Thank you for showing us Loki. That's a cute little pup.
Hi.
And then Paulina, we've been trying for this for like multiple class periods, right? We finally did it today.
Yeah, that's Mowgli and Baloo.
Mowgli. Oh, I know. I know where you're coming from on that one.
Yeah.
Oh. They both look sweet. So it looks like they're outside pups.
Yeah, they were just napping outside in the sun, so I just kind of interrupted them.
This seems to be the theme, I think, is like napping pets. This must be prime nap time.
Yep.
So did they get along well, both of them?
Oh yeah, they're best friends.
Oh, that's pretty cute. Thank you so much. I'm glad we finally caught them. Anyone else have anything that they want to share? All right, not too bad. I am very pleased with our situation. Yes, nap time, noon nap times for sure. I know it's kind of killing me too. I really didn't want to do it. And then the Tiger Cam, that is the only time that the tiger was here. And then your colleagues, they basically made me do it. I don't know if I can handle it. Okay, so I noticed on last lecture, it wasn't a good idea to do the screen sub shot, so I'm just gonna do the full on thing so that our little viewing stuff shouldn't be in the way this time. So let me do a quick switcheroo here and share. Okay, let's do a new share. Come on, Zoom, let's be helpful. There we go. Okay. No, still, here we go. Sorry. It's like the first time I've ever done this. Okay. So let's get iPad rolling. Yeah, PowerPoint. There we go. Okay, cool. So how does this look to you? Again, this is a little bit different. What all do you see? Let me get chat where I can see. That's the only reason I don't like this super a lot. Do you see faces in the way of this? Okay, let's see. We got, yes, please email me all of your pictures of your pets. I will be into that. Our slides blocked through your beautiful faces in this view, or does this look okay on your end? I think this probably should, okay, good. Okay, fabulous, neato. Thank you all for that. Okay, so you can't see yourselves. Well, I'm sorry, because you all are just beautiful people. So your loss, but my gain. Okay, so here's what we're gonna do, just like we talked about last time. Everything is on the table. You can ask me about anything. If there's a lull in questions, which you can either ask through chat or by unmuting yourself, whatever makes you happy, we'll do that. If there's a lull in the questions, and again, it doesn't have to be a specific question. It could be, hey, I need you to re-explain this slide on lecture, blah, blah, blah. That is totally fine too. And if there's a lull, I'm just going to go through these individual questions. I'm not on the iPad, so I'm feeling like things won't blow up here in about, an hour. But it also means it can't color as much or at all. So that is a little bit annoying, but hopefully this will kind of work out okay. Okay. So does anyone want to kick things off with a question? And if not, I'll get started on this question here, which is kind of where we picked up from last time. We kind of jumped around a little bit. Okay, so as you all are thinking and typing and all that good stuff, I'm just going to roll through this. So this is going to be, yes, I'm glad that you mentioned that. I think on maybe one of the, what are those called? The guides for the exam guides, I think it talked about ping pong and all that kind of stuff. Just this year, there's a few things that I cut out just because of time and blah, blah, blah. So we're not going to be tested on that this semester, so you can ignore that. So don't worry about any of the ping pong, sequential, random, all that good stuff. We will not be tested on that. Thank you for asking that. That's an important point. Okay, so this is something that you will be tested on. This is basically how we can use this Nernst equation to figure out about the Gibbs free energy that's associated with transport. And so this is a question that's going to be on your exam. It's super easy to use, but it's kind of an intimidating looking equation because there's a ton of variables. But I just wanted to take a quick moment to go through that. Okay, so what are the key things to think about? It's going to be obvious when you use this equation. It's the only time we're going to be talking about transporting ions and charge and a bunch of millivolts and things like that we're not used to seeing in other equations. So what this is asking us to do is calculate the change in Gibbs free energy. So we're going to be solving for this delta G right here. So that's neat. And then we've got R, which is going to be helping define our units here, right? So anyway, let's go back up here. Across the plasma membrane into the cytoplasm. So we're going from extracellular to intracellular, or outside to inside. The sodium concentration outside the cell is 2 millimolar. Sodium concentration inside the cell is 0.400 micromolar. Now this is going to be a situation where it doesn't matter what the units are as long as they're the same. So check this out. In this equation here, you're going to see that those units are going to cancel. So we're going to want to make sure to convert one of these into something else. So it looks like for me, this is going to be easier probably to go ahead and put this into 2000 micromolar and keep this at 0.4 micromolar. Okay, let's see if there's anything else we need to be concerned with. So R is going to dictate some of our units. We need to make sure we're in joules and Kelvin and moles. Okay, so far so good. Temperature, that's going to be something we're going to need to convert, right, into Kelvin from Celsius, or I'll never put it in Fahrenheit because nobody needs that. And then you just have to figure out concentration of these two entities inside and outside of the cell. I'm actually just going to go ahead and flip to the answer slide. So we should easily be able to hopefully pop in those values here. You can see that we have the same units. And again, I've converted both of these into micromolar, but it wouldn't be wrong to have them both in millimolar, just as long as they match. Here's one thing that you want to pay attention to. So this Z is related to the charge. So if it depends on the ion we're talking about. So here we're talking about sodium, so it has a charge of +1. So that's easy, right? If we were calcium, we would be multiplying this part of the equation. We'd be multiplying that by +2. If it was chloride ion, we'd be multiplying that by -1, right? So it's going to depend on the ion. Okay, so that's so far so good. Faraday is another constant. It's telling us that we need to make sure that we're in joules and moles, but importantly here, volts. So you see that this membrane potential, this is often written in millivolts. So make sure to convert that to volts. You can see that I've done this here. Pay attention to that charge too. Everything else is just sort of a plug and chug, as they say. And oftentimes the joule, it comes out in joules per mole, and often that's a bit cumbersome. So you'll see that I'm often asking you to put this in terms of kilojoules per mole. If you have any questions on that, let me know. In the meanwhile, I'm going to run over to question 9 because we got a question about that. So 7, 8, 9, here we go. Okay. So which of the following is true for both primary and secondary active transports? We're looking for true answers. So let's figure out how we could make the rest true, and then we'll talk about the true answer. Okay, they are not very specific with respect to the substrates they transport. No way. Remember, these are usually very, very specific. So they can even often distinguish between two ions that we might say are very similar. So, it can distinguish between calcium ion and potassium or sodium, things like that. So these are very, very specific. So that should come up as false. Next one, they catalyze ATP hydrolysis to pump a substance against its concentration gradient. If I asked you about primary active transporters, that answer would be true. But I asked you about primary and secondary. That's not true with secondary. Remember, secondary is coupling either a sym port or an antiport, right? Those are coupling a favorable ion transport with an unfavorable ion transport. So this would be true if I said only primary active transport catalyzes ATP hydrolysis to pump a substance against its concentration gradient. C is they couple transport of one substance against its gradient with co-transport of a second substance down its concentration gradient. Again, this would be true if I was only talking about secondary active transport. And ATPases, ATP pumps, those don't necessarily have a second ion. And certainly if they do have a second ion, one isn't favorable and the other is not favorable. That's not the setup. You're usually pumping both against a gradient and coupling that to ATP hydrolysis. So C is only true for secondary active transport. Does that help, Natalia? Okay, and it looks like we've crowdsourced Crystal's question. And yeah, that looks like a good answer for that. So that was just making sure, being really careful on all those different units. Let's just take a quick peek at that. As you can see, we had to be really careful to change units on making sure that we are either both in micromolar or both in millimolar. Either way is fine. And then making sure to change the units from millivolts to volts. Okay. So we got another question here. Go over what it means when a lipid is fully reduced, as in a concept. Yeah, absolutely. So I'm not sure if I have any good lipid pictures right here. So I'm actually just going to go to this question where we're looking at this one here. Okay, because I can kind of make points off of this slide. Okay, so whenever we think about reduction, right, this is going to be gain of electrons. We're going to think of hydride or hydrogen rich. When we think about oxidation, that's going to be loss of electrons, and that's going to be more oxygen rich or hydrogen poor. That's how we can sort of loosely sort a more oxidized versus a more reduced. So when we're talking about a reduced fatty acid, we're going to be talking about hydrocarbons that don't have double bonds. They have all of the hydrogens present possible. And so in this example, fully reduced lipids are going to be steric and palmitic acid because they have no double bonds. They have basically the maximal amount of hydrogens present on each carbon. Now, linoleic acid and this EPA acid, those are a little bit more oxidized or less reduced because you can see that there's some double bonds present. And so we've essentially removed a couple of hydrogens that allow these double bonds to form. And so if we were to go through and think about getting the most energy out of this, we get the most energy when we go from the most highly reduced and take that down to the most highly oxidized. So we want to start with the most reduced thing that we have. So B and C are the most reduced things that we have, but we have more carbons to reduce in B, essentially. We have more hydrogens that would be available for oxidation during the breakdown process of these fatty acids. So this one is basically gives us the most energy because it, like palmitic acid, is as reduced as could be, but it has even more carbons, hydrocarbons available for that oxidation process. Does that help, Laura? Okay. While you all are thinking about additional questions, and again, it can be conceptual, it can be on this, it can be on something else, all these things are on the table. So hopefully this made sense for this question here. We talked about this one last time, we talked about that one last time, same goes for this one. This, I think we haven't talked about, so let's take a quick peek at this. So we're looking for characteristics of enzymes, right? Which are the coolest of all of the biomolecules, if I may say so myself. So what do enzymes do? And I'm going to move this group chat just because I'm so paranoid that you're going to see this in the slides, in the recordings. Okay, so what do enzymes do? Let's go through each of these questions in turn, and I'm just going to go ahead and pull up the answers so we can kind of be on the lookout for what we're thinking about. Okay, first option, enzymes lower the free energy of activation. Every single enzyme. How many enzymes? All of the enzymes. All of the enzymes? Yes, all of the enzymes. This is a strategy that every single enzyme uses in order to make the rates go faster. And the way that they make those rates go faster is by lowering that delta G double dagger, right? That's the free energy of activation. That's basically stabilizing the transition state. Everything that I just said, same thing, same idea, just different ways to say it. What are some other things that all enzymes do? Proximity and orientation. Those are also two important concepts, and we'll have to wait and see if those are actually represented here, but every single enzyme is going to use proximity and orientation. Those sound like the same thing, right? But they actually are different. What proximity is basically, let's see what we got to. I guess we're back to the candle holder. Really don't. Oh, no, I got something. It's a little bit bigger and it's going to be easier to see. I have this bowl. Oh, come on, Tiger King. Okay. So I got this bowl and I have this substrate, right? And we're basically aiming for this. And so basically what we could think about is in the concept of proximity, right? We could have a situation where my substrate is like way over here. You can't even tell what's going on, but it's way, way over here, right? It's not close. The local concentration of the substrate is low, right? Because this enzyme basically isn't even really seeing any substrate. But proximity is basically saying, hey, you know, the substrate's in the area, right? Is it perfectly positioned in the active site? No, but it's in the area. The local concentration is high. Okay, what's orientation? Well, orientation, and unfortunately this is a really crappy substrate, so let's instead use this little piece of coral, right? Let's say that the substrate has to be in this position, not like this. So this may be proximity, right? But this is orientation, where it's perfectly positioned in the right spot. The electron orbitals are positioned perfectly so that this is able to effectively bind in the right place, the right orientation in the substrate for catalysis to happen. Okay, mild tangent, but worth talking about. Okay, enzymes lower the Gibbs free energy. Do they do that? No. Do they ever do that? No. No, 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 no. That has to do with thermodynamics. That's the starting place. That's the ending place, right? That's telling us spontaneous versus non-spontaneous. So 2 is never, never, never true. Enzymes usually have wide flexibility in the pH, temperature, and pressure conditions at which they function. So who recently has had a body temperature of 270 degrees and and 5,000 ATMs pressure and a pH of 2. No one has that, right? We have a very bossy limited range that enzymes work. It's going to be physiological pH, physiological temperature, and 1 atmospheric unit. So we're really limited in what they can do. So that's not true. What else we got? Catalyzes single turnover, i.e. cannot be regenerated. No. Remember, we have to be able to turn over. What's turnover? Remember the turnover number, kcat. The idea of turnover is converting substrate into product. So no, by default, it has to be able to regenerate itself so it can go on again. You're not saying that, I saw an oh no, does this mean I'm breaking up? Please don't tell me I'm breaking up. Otherwise, Tiger King is going. Okay, very good. All right, increase, okay. Oh, okay, good. I'm glad to hear. Please get some ice, Jasmine. Cool yourself down. Increase, all right, so we know that number 4 is wrong. Increase the rate of both the forward and reverse reactions, i.e. increase the rate at which the system comes to equilibrium. Yes, all enzymes do that. They increase the approach to equilibrium. We reach that equilibrium much, much faster. And that's another way, just like lowering the free energy of activation, that enzymes do. So 1 and 5 are the only ones that work. Okay, so let me check in on chat and make sure. Okay, very good. So far, so good. Let's see what else we got going on here. Okay, we just went over this question. Let's check this out. Okay, so what is this telling us? Say the concentration of potassium ions is lower outside the cell and higher inside the cell. Opening of a potassium ion channel will therefore cause K+. Okay, let's pause for a second. Do ion channels work with their concentration gradient or against their concentration gradient? They work with their concentration gradient. Remember, ion channels are ones that we talked about whenever we were discussing facilitated diffusion, right? This is a passive process. It is not an active process. So anytime I'm asking you about ion channels or ionophores or porins or any of this kind of stuff, you're going to be thinking going from an area of high concentration to low concentration, no energy required. So I told you it's higher inside. This thing better be flowing from inside to outside. It should be going from high concentration to low concentration. So I'm already looking for, with its gradient, I'm going to eliminate A and C right out of the bag. And I said it's higher inside, so it's got to be going outside the cell. So I'm going with B. That sounds like a reasonable answer to me. Okay, and what do you know? It was right. Phew. Okay. Let's see what else we got. Let's just keep rolling on. And yeah, so what does it mean? Yeah, that's a really important question. So the question is, what does it mean when the concentration of enzyme is saturated with substrate? So that is an idealized condition in a world that we all wish we lived in, where we're assuming that every single enzyme, so let's say I have a test tube of 500 enzymes, and every single enzyme in that test tube is doing its job. It is bound to substrate, it's turning it over, it's immediately binding substrate, turning it over into product over and over and over again, and every single enzyme is doing it, all 500 of them. If that's happening, the velocity that we would measure of product formation would be Vmax. If that is happening, the rate of product formation would be kcat. So if we have an enzyme that is fully saturated with its substrate, I'm basically telling you, hey, this rate I'm about to tell you is a kcat, or this velocity I'm about to tell you is a Vmax. In real life, we never have enzyme fully saturated with substrate. There's always some misfolded enzyme or just enzyme that's just not doing, stuff as well as it ought to. Whatever reason, we never get full saturation. Does that help, Alexandra? Okay, great. So which membrane protein type is most likely to have a hydrophobic region on its surface? Okay, so let's think about this a little bit. So obviously, we need to know different types of enzymes or proteins and where they're found. Remember, a peripheral, let's go back to our bowl, and here's our enzyme. So let's just say, oops, the tiger ate the bowl. Okay. So let's say that this is one edge, right? So this is liquid water, and then this is the membrane, and then this is the other side. So this is out, inside the cell, let's call this outside the cell, and this is the membrane. Okay, so let's say, for example, I have a peripheral protein, right? And so it's going to be just associated with the membrane. So what is the surface of this protein going to look like? Well, it's going to look like any soluble protein because it's mostly surrounding water, right? And it is attached, it is associated with the membrane, but it's associated with the polar part of the membrane. Remember the hydrophilic head groups on those glycerophospholipids, right? So this thing has hydrophilic or polar residues all around the outside, just like we often think, right? Okay, so then let's say I have a lipid linked, right? So here's my lipid linked protein. What do you know? I actually have a little hole here. So let's say that this little lipid tail is down in this hole, right? But a lipid linked is just simply that. It's just a little lipid tail that attaches the rest of the protein. So it's the lipid linked protein is also going to have hydrophilic regions because you can see it's fully exposed to liquid and it's abutting the polar part of the glycerophospholipids, and it's only the little string of lipid, right, that's going into the membrane. Okay, last example is an integral protein. What happens in the integral protein? Well, remember, it goes all the way through, right? It goes all the way through the membrane out the other side. And so we're going to have part of that protein is actually going to be polar, right? It's going to be polar. And this part on the inside, of course, is going to be nonpolar because it's actually within the membrane itself. So it's only going to be integral proteins that are going to have hydrophobic regions on the surface. Okay, questions for me or concepts to re-go over? I'm just going to keep rolling through these, but I really love it when you ask me questions, so please don't be shy. Hey, let's do this. Yeah, this looks like something that could be fun to do. Okay, so check this out. I'm wanting you to identify what is going on in a protein. And oftentimes I'm going to ask you in terms of residues. So make sure that you still have access to amino acid structures so that you can identify which amino acid I might be referring to. Okay, check this out. This is not one of those cases though. So the following diagram shows a portion of reaction of an enzyme. What type of catalysis is occurring in the step? Okay, so maybe you're saying like, holy crap, where's the enzyme? What's the substrate? I'm so confused. And then you calm down, you take a step back and you realize, okay, look at all this. This is all enzyme, right? And here's my little substrate bit. And so I'm going to be thinking about what's happening from the perspective of the enzyme. Is the enzyme acting as an acid? Is the enzyme acting as a base? Is the enzyme making a new covalent bond? Does the enzyme have a metal associated with it? Blah, blah, blah. Okay, so let's check this out. What's happening here? Well, this doesn't look like anything interesting. What's going on here? Well, I see that I have a nitrogen here that is fully bound up with hydrogen, so much so that it has a positive charge. That means we are not in the market for picking up a proton, but we're definitely in the market for donating a proton. And that's exactly what's happening here, right? You can see that the substrate is going to be picking up a proton that's being donated by this part of the amino acid. And you can see that I have a transition state that's forming here. I don't see a covalent bond forming between the enzyme and the substrate. So what am I going to call this? Well, I'm going to be calling this acid catalysis because I'm donating a proton. Me, the enzyme, is donating a proton. Okay. Be sure to let me know if you have questions on that. So what's this? Okay, now we're looking at a similar type of question where we want to see what type of catalysis is going on here. Okay, so let's orient ourselves. Where's the enzyme? Where's the substrate? This is an easy one, right? Because I'm still just sort of labeling it. But you should be able to tell because either I have labeled it as such, like here, or you will see an amino acid residue present and something that is definitely not an amino acid residue. This could be nebulous, right? If I didn't have this labeled as substrate and this wasn't labeled as enzyme, you might have an argument where maybe this could be a substrate, maybe this could be an enzyme, but it's labeled here because it was a little bit ambiguous. Okay, so let's see. Yeah, I know, right? I wish I was a fresher on my OChem. Okay, so what are we looking for here? Well, we're looking for, maybe we start off with acid base. Let's see if there's any of that going on. So we're clearly not going to be donating a proton, but maybe we're picking up a proton. Is that what's happening? Nope, that's not what's happening. Instead, we're having a nucleophilic attack of this oxygen on this more electrophilic carbon. Okay, well that sounds a little bit covalent catalysis-y if I had to say so myself. And let's go over to the transition state. Holy crap, would you look at that? It's a new covalent bond that now we have the substrate, which is this part right here, and this part, the enzyme, right? New covalent bond with it. So this would be a great example of, you guessed it, gang, covalent catalysis. Okay. Yes, they're very complex feelings when you think about organic chemistry. I have also very complex feelings about organic chemistry. Do you all feel confident about writing rate laws? You need to think about that question while we talk about this. And actually, we talked about this one last time, so I'm gonna skip this one, but I'm gonna want to make sure that you all feel good about writing rate laws. Yeah, great. What do you know? How about writing rate laws? Yeah, I think, yeah, everyone remembers it perfectly. Let's just all walk away. Okay, so what I am gonna do is, wish me luck, crew. I'm gonna come out of presentation mode real fast. I'm gonna make a new slide, and I am going to color on it. Yeah, like that's gonna go well with a mouse. So guess how that's gonna work. Actually, let's do the touchpad. That may be less horrible. Okay, so let's just start. Oh man. Okay, let's do this for a second. Okay, let's do. Bear with me for one quick second. I missed the iPad. I'm not gonna lie, but we all know what happens when we iPad. Okay, so let's just do the quick Michaelis-Menten setup. No, you know what? You have examples of that in your notes. Let's do something else. A plus B goes, let's make that an equilibrium, goes to AB, and then let's make this an equilibrium because, go nuts, life's short, goes to C plus D. Okay, all right, so, and I actually might even be able to do this in text. So consider yourselves super lucky. Okay. All right. So let's do this. Okay. Hopefully you can all see this. Okay. Right. This, yeah, I think you can. Okay. All right. So here's what we're going to do here. Let's say that I'm interested in the rate law associated with the rate of formation. So small d, thank you, PowerPoint, I know better, divided by dt. So what I'm asking you is, what is the rate of formation of AB over time? And you'll notice I wrote AB in the same brackets. That means just this entity. If I was talking about A and B separately, then those would be in separate brackets. That would be A and B, right? So I put this purposefully as AB in the same brackets. Okay. So, all right, let's go for this. So whenever you're gonna write a rate law, what are you gonna do? Well, you're gonna figure out what I'm asking you for. And I'm asking you for making AB, right? The screen camera is blocking half the slide. Thank you. This is always the thing I'm worried about when I'm not in this mode. Does this help whenever I minimize you all? Thank you for letting me know. That's so important. Does this help for the videos, the camera stuff? Samir? Is that good? No, yes, it helps? Okay. All right, great, thank you. I noticed that on the last time and it really was bothersome. Okay, and I'll also kind of scooch it too because I think it tends to put it on the right. Okay, super, thank you. Please let me know that every single time because this will happen in the recording if you don't. Okay, so what you're gonna do, thank you everyone, what you're gonna do is you're going to figure out what are the things that are helping me make AB and what are the things that are making me lose AB. What you're gonna do is you're gonna find all the arrows pointing towards it and you're gonna add together those rate laws. and you're going to find all the things pointing away from it, and you're going to subtract those rate laws, because the arrows pointing to it are making it. That's helpful. The arrows pointing away from it are consuming it. That's not helpful. All right, so let's begin. What's our first arrow that's going towards? Let's do all the going towards first. Well, the first one, right, is just simply this beginning step, the top arrow that's pointing towards that. So how am I going to write the rate law? Every single time I write a rate law, I multiply the K associated with that arrow times the substrates every time. Is it ever times the products? No, it never is. It is always times the substrates. So what do I got here? Well, I got K1, right, because it's the first arrow. And what are my substrates? Well, my substrates are A. Am I done? Heck no. They're also B, right? That's my first situation. Now I'm describing this thing here. Okay, do I have any other arrows pointing to AB? Yeah, I do, right? This reverse arrow here. C and D are going in this direction to make AB. Okay, well, I put in a plus because it's also a helper one. And what's the K associated with that? Well, I got K1, K minus 1, and I got K2 and K minus 2. So that means it's going to be a K minus 2, right? Okay, so let's put in K minus 2. And what am I multiplying that by? Well, by its substrates, just like always. What are its substrates? C, okay, and D. Oops, and D. Okay, all right, so those are all the helper reactions. Those are all the things that are making AB. Do I have things that are taking me away from AB? Yeah, I do. So I'm gonna minus those, subtract them. And what's a non-helpful arrow? Well, one non-helpful arrow is AB going away, right, to return to A plus B. So how do I write that rate law? Well, I got K1 on the top, K minus 1 on the bottom. So I'm gonna subtract K minus 1 times what? Well, what are my substrates? My substrate is just AB. So I'm going to multiply that by AB. Yes, let me catch that, Natalia, in one quick second. Let me just finish this up real fast. Do I have any more arrows that are associated with taking me away from AB? I do, right? And that's this forward direction here. So I'm gonna subtract that. I've got K1, K minus 1, K2, K minus 2. So that means I got a K minus 2. And what's my substrate? Again, AB. Okay, so the question is, how am I naming these darn arrows? Well, the convention is you just count them. And you name all the forward ones with a positive number, and you name all the reverse ones with a negative number. So the very first arrow is always going to have some form of 1 associated with it. So the top one is going to be K1. Oops, I don't know. That's not what I meant to copy. So this top one is going to be K1. And what's the bottom one going to be then? K minus 1, right? And it's a big K because it's a jerk. Should be a little k, right? I could describe this whole thing as an equilibrium, right? I could call it a KD. Okay, so let's do the next arrow. What am I going to call the top arrow? The forward arrow, right? And this is stupid because you can't tell which one is forward and which is reverse. But the top arrow is going to be forward. The bottom arrow is reverse. That's a convention. Okay, so what do I got here? I got a K2 on top, right? And then on the bottom, I got a K minus 2 because, again, I'm going backwards. Okay, and now there's a question. Can I write steps on that? Can you help me what you mean, Krima? Can you write steps on that? I think I might need a little bit of help understanding. In the meantime, I'll get a question. Isn't the last one K2 times AB? So you're right, I have 2 K2s, something is wrong here, but let's see where I screwed it up. Sorry, good eagle eyes. All right, so K1 should be A times B, then we're gonna add K2. Yep, actually this is where our problem is. No, we're because we're doing reverse. No, that's okay. So C times D is the one in the reverse, minus K minus 1 times AB, and then yes, bingo, thank you. K2, good. Thank you so much, Avery. That's exactly right. So what happened? Why did I just screw that up? Okay, so let's go back to that particular one. Let's actually do both of these just to really highlight the point. Okay, so this one here, we know that we covered all of the rate laws that are helpful, all of the rates that were helpful that make AB. K1 going in the forward direction, that makes AB. K2 in the reverse, K minus 2 in the reverse reaction makes AB, right? So both of these are gonna be added. A plus B times K1 and C times D times K minus 2. Okay, now we're looking at the rates where the arrows are going away. So one of those is going to be K minus 1 times AB. That's this one here. This is for this arrow going away. And just to kind of clarify this real fast, check this out. This just will kind of emphasize the away arrows are on the bottom. And then the forward arrows, boop, 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 are going to be on the top, just to make those arrows a little quicker. If you see arrows like this on the exam, know that this is the convention. Forward on the top, reverse on the bottom. And if you forget, just ask me on the exam. Okay, so this next one here, K2 is taking me away from AB. That's not helpful. That's why I've subtracted it. So I'm going to take K2, multiply it by its substrate, which is AB, and that's how I got my rate law. Can I please move the screen to the left? Yes, does this help? I'm not sure. It limits me. Okay, yeah, it limits me a little bit of what I can do in this mode, which is why presentation is better. Okay, can you explain by writing step by step how you did the rate law on this example? Yes. So basically, let me do a different part. So let's do, for example, let's say that I asked you, so this is the solution for this one. So I'll leave that up there and you can look back at that on your own time. Let's do another one so that I can take you through this step by step again. So let's say what the change in concentration of C over time is. So now this is your new question. Okay, so how would you write that? Okay, so I never, so for Laura, I wouldn't have you do that. It would always be a single entity. It would never be two entities. So it might be the rate law for AB complex, or it might be the rate law for A, or it might be the rate law for B, or it might be the rate law for C, or it might be the rate law for D, but it would never be a separate A times a separate B, or a separate C times a separate D. So I won't give you that example just because that's what we don't do those types of things. Yeah, okay, so let's do the one on C. All right, so how do we go about doing this? Well, what we want to do is we want to find all of the C's in the equation. Well, that's easy. We just got one, right? Okay, so then what we care about is what are all of the arrows that are making C, and we add those things up, and what are the arrows that are taking us away from C, and we subtract those. So what are the arrows making C? Well, the arrows making C is associated with K2, right? AB going to C plus D. So how do I write the rate law associated with K2? Well, let's start off by multiplying K2. What are the substrates for K2? Well, the substrate's AB. That's the substrate. There's only one. So I'm going to add that because I'm making C, right? Okay, what's taking me away from C? Well, K minus 2 is taking me away from C. So that means I got to subtract it. Oops, not sure where that happened. That means I got to subtract it here, right? So I'm subtracting this next one. And what are the substrates for K minus 2? Right? Well, let's put down K minus 2. And the substrates are C and D. Right? Does that make sense? Okay, so the question is, why do we include A plus B and only AB for making C? Well, because yeah, it's totally true that in order to get to C, we needed to make AB, and we got AB from going from A plus B. But we only write things that are directly related to C. That's it, right? So in AB was in the middle of all this business, right? There was every single arrow is involved with AB. K1 makes AB, K minus 1 consumes AB, K2 consumes AB, K minus 2 makes AB. But with C, K2 makes C, and K minus 2 takes away C. Okay, so hopefully that helps Laura. And then would it be wrong if we added starting with K1 versus K2? Is this in the relationship, Natalia, in the AB example or the C example? In the C example. Okay, so would it be wrong if we added starting with K1? No, so K1 is not at all involved in the C example. You basically can ignore this whole spiel right here. You only care about the arrows that are directly touching C. They can be pointing towards C or they can pointing away from C, but they gotta be touching it. Similarly, hey gang, oh good, I'm glad to hear it, Crystal, with the arrows being helpful, but please know it's kind of a pain in the ass, or it's hard to get Google Sheets. Actually, I can't, making Google Sheets do this doesn't work so well. So you're gonna see arrows like this. So just ask in class, be like, hey, I don't remember if the forward arrow is on the top or the forward arrow is on the bottom, and then I will make an announcement in class. Or just write a sheet that shows, basically this type of setup, whatever you wanna do. Okay, let's do this last rate law example where we have the change, we have the change in, what's the last one we could do? D, you wanna do, just for funsies, you wanna do A? Does that sound like fun? Heck yeah. Okay, so let's do that. Okay, and I'm just gonna scroll through and make sure we got everything. Okay, and Jasmine's gonna have a question too. Let's do Jasmine's question first. So D, change in C over time looks the same as change in D over time. Yeah, great question, Jasmine. So basically the question is, what if I was doing the change in, dang it, okay. D, I am just out of sorts here. Stop it. Okay, D over dt. And that's point is exactly right, right? So you can see that it's, it's on the same, arrow scheme. We don't see D anywhere else, right? So it's gonna look exactly the same as what we had written for this, right? And we're about to do this example of dA. Well, the answer is going to be the same solution if we were doing the change in concentration of B over time. So let's do this one real fast. How am I going to write rate law for the change in concentration of A over time? So I'm looking for free A. What are the arrows that touch free A? Only these two. So am I going to be talking about K2 or K minus 2? Nope. If you see this on the exam and I'm like, oh, write a rate law, and your brain just exploded and you forgot how to do that, at least look to see, if I ask you about AB and you see 4 arrows involved with AB, you should see 4 things, right? Four little chunks of blah, right? If I'm asking you about B, you only see 2 arrows touching that. You're going to be looking for only 2 chunks, right? So that will help you eliminate things right off the bat, even if you forget all the everything, okay? So let's look at A. What arrows are touching A? Well, K1 and K minus 1. We're not at all going to think about K2 and K minus 2. So who is helping make A? Well, K minus 1 is helping make A. So that's going to be the term that's added. So let's put in K minus 1. What are the substrates for K minus 1? Well, AB is, right? That's at the head of that arrow. So I'm going to type in AB here. What's going on with K1? K1 is taking us away from A minus B, so we're going to subtract it. Okay, so that's K minus 1. What are the substrates for K minus 1? Well, it's A and B, right? So that's how we write the rate law for that. And guess what, friends and neighbors? Same darn thing if we were asking about B. Do we feel solid and happy about rate laws? I think I heard a rumor on the street that writing some rate laws might be on the exam. So all right, rate laws. I'm gonna go ahead and save this slide and I'll upload it and then you all can see what's going on there. Okay, so I'm gonna go back into presentation mode because it's kind of annoying for you all and high risk of what you're actually seeing. So let me do this. So you should see nicely now, right? Okay, great. I'm gonna just be waiting for you to ask questions and then oh yeah, good idea, I could title it. Yeah, I could do, yeah, so people that weren't able to view this won't be like, what in the hell is she talking about? Okay, so let's just call this how to write a rate law. Okay, great. Good idea. Okay, so let's do this. All right, so did I go over 20? Question 20. Question 20, right? Here. I don't know. I don't remember. I think it might have been an office hour, so not really here. So let's go over number 20. Let's do this. Okay. So we're talking about a second order reaction. So you know what I would do, and I think I might have already mentioned this to you. What I would do is I would go over to wherever that was in lecture, where it was basically a huge list of rate laws. Let me see where it actually was. I think it might have been lecture 23. Yeah, okay. So if you go to, let me actually, I'm gonna close this out real fast so it will reshare this new one, I think. And give me one quick second, sorry. Okay, PowerPoint. So here's what I would do, and this is the COVID-19 prize, right? Is I think I would just have this slide handy, honestly, because normally the way that the exam format is giving you, it has it all mixed up and you can't tell which of these is for first order and which is for second order. And normally that's the part of the exercise is to get you to know that. But the world is on fire and everyone deserves a prize. So if I were you, I would just have a screenshot of this handy, and I would use this to help me answer questions when I was looking at, how to use, how to make a linear plot, right? Or how to use a half-life equation, something like that. So pro tip from me to you. Okay, so let me X that out. So that is, let me check in on this chat, see what that was. Yeah, clutch, totally clutch. So that was lecture 23. So take a gander at that. Okay, so let me get back to where we were, number 20. Here we go. Okay, so am I still sharing with you? Okay, great. So here's the moral of the story. So part of this was getting you to figure out how to use the appropriate rate law for this situation. So I'm actually going to go ahead, since I can't really color on this so much, I'm going to take us to the answer slide. So the series, what you would do, what you're going to do here is you're going to identify the reaction order. Okay, well, how on earth do you do that? Well, you count the substrates, right? If you have one substrate present, you've got a first order reaction. If you have two substrates present, even if they're the same thing, you are probably going to have a second order reaction. Why do I say probably? Is there any exception of a two substrate reaction where it's not second order? Well, yes, yeah, bingo. If I specify that it's pseudo first order. Have I said anything about pseudo first order here? No, I have not. And in fact, I even told you that it was second order, but normally I'd be a big jerk and I'd actually make you want to answer that yourself. So if you saw just for the reaction A plus A goes to P, and you don't see anything about me calling it pseudo first order, you're going to use the second order rate constant rules and equations and stuff like that. If I say pseudo, you're going to use first order. Does that make sense? Okay. So these are the series of equations you're going to use. So let's actually go through this. So you should actually feel okay writing this rate law. We just went through it, and we're asking basically about the change in concentration of A over time, right? So we know now that kind of the arrow, the charge basically kind of makes sense. So check this out. If we were to ask you about the change in concentration of A over time, what would we do? We would say K1, because that's the only K that's present. This is an irreversible reaction, right? Times its substrate. So K1 times A, right? But is that K1 making A or taking it away? It's taking it away. So we would technically subtract that. So this is that rate law that you all should feel pretty good in writing. Now check this out up here. We could also say, what is the change in disappearance over time? So we're already acknowledging that it's taken away, and that's how this ended up not having a negative. But this is how we've been talking about putting together this rate law. Okay, if you don't tell us it's pseudo, we can't assume that it's pseudo, right? That's right. If I don't say that it's pseudo, don't assume that it's pseudo. If you feel unsure on what to do on the exam, you can say, is this pseudo first order? And I'll say probably something along the lines of, I don't see any evidence of that, So yeah, I will have to explicitly tell you that it's pseudo first order. You should not just assume that if I'm asking you to write rate laws. Now, if you're doing Michaelis-Menten kinetics, right, you are essentially assuming that type of thing, but I'm not gonna, don't even worry about that part. I'll tell you if it's pseudo, and if it's not clear, ask me on the exam. Okay, so I'm gonna be using this rate law equation, and because I don't think anybody feels like doing calculus right now, we're gonna use the integrated form. Call me old-fashioned, but hard pass on that, am I right? Okay. So what we're going to do is we're going to look at things to plug in for this integrated rate law. Okay, so starting concentration of the reactant. Okay, well, what's that? This A0, do you remember we would have a couple of different subscripts that we would put there? Remember what sometimes we would put a T, right? Remember E in parentheses with a T? That means total enzyme concentration. What does the A with the 0 mean? That means initial, starting at that initial moment. How much substrate concentration do you have? That's exactly right. Okay, so what is our initial starting concentration? Well, that is 0.95 molar, right? Okay, so I'm going to be popping 0.95 molar into that. Now remember, these units are going to have to match, right? So whatever's going to be spitting out to me is going to also be in molar. Okay, so 0.9 molar going in here. You can see that, right? So 1 over that. What else we got going on here? A rate. Okay, neat. And it is indeed a rate. I see it's just units of per time. What kind of rate, does rate order does that sound like for us of just a per time? Don't look, that may be too much. That's okay. Let's I retract my question. Okay, so this K, we're just going to pop in 19 per second here, and this T is simply time. So I got to convert. I have to convert. Do I need to actually? Am I making you convert time? Are you okay to not convert in time? Oh, I'm sorry, not temperature. Look, I screwed myself up. time, and then I'm looking at the temperature. Yes, so a K is going to be this rate here, 0.19 per second. The T is going to be time, which I'm telling you is 100 seconds. So these units need to cancel. If this is in minutes, you need to convert this into seconds, right? So it matches your rate. So what I've done here, 1 over 0.95 molar, that's my 1 over starting substrate concentration. Adding, because that's what the equation says, my rate times the amount of time that has passed, right? And I made sure that these units are going to cancel. Okay, so what does that end up giving me? Basically, this gives me some type of value. I end up mathing my way along, and I ultimately get myself towards the A concentration. So that's this after 100 seconds. That is something that you could plot potentially onto a Michaelis-Menten plot. You could say at 0.050 molar, I had a rate of 0.19 per second. Okay, yeah, that's a good one to go through. So I might ask you how to do, no, the temperature doesn't matter in this question at all. The rate laws never use temperature, they always use time. If you go back to that other example, that slide that I showed you, here's a half-life, right? Again, this is looking at that. This is actually a good one to do too. Let me just scroll back real fast and see, because I think we're almost there anyway. Yeah, and I'm actually going to rearrange this slide real fast because this is right in the middle of the answer, and that's kind of confusing. Okay. All right, so let's jump back up and hit, actually, I think, did we already do this one? I think with serine and figuring out the type of catalysis we did. Okay, yeah, that's what I thought too. Okay, All right, we did this. This is the weird one, right? Remember where we're figuring out converting KCAT to Vmax. This is one you're going to want to know how to do. This one we also did in class. Okay, great. That's where I wanted to get to anyway. So this is a question that's looking at half-lives. And again, it's going back to that same chart where you'd have to figure out what type of half-life rate law to use. And your only choices are going to be first order or second order where the substrates are the same. And guess what? Good news. You have a situation here where you have a second order reaction, so you have two of the same substrates. So you're going to use the second order rate law equation in this case. So if you look at that chart, you know you're going to be using this. If this was simply x goes to y, this would be a different scenario, and you would be using this rate equation here. So how would I do this? All you're going to do is you're going to take that equation and just plug in the things that you need. Okay, so this is basically the K, right? This is our rate. So in this case, we've got second order rate constant 3.6 times blah, 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 big giant number. That's neat. This is our starting substrate concentration. So that's going to be 6 micromolar. But is that going to play nicely with our rate constant? Nope, it's really not. You might hear a little bit of things in the background where our television broke, which obviously is sad news during quarantine time. And I think someone's going to come visit and fix it. So that's happy news, but don't mind if you hear a little chatter in the background regarding fixing a television. Okay, real life in quarantine land. Okay, so here's what's happening here. We have our starting substrate concentration, but it's got to play nicely with this rate constant. And that means the units need to be appropriate. So in this case, I'm in per molar. I need to get this into molar, right? So I'm going to convert that times 10 to the minus 6, which allows me to get into molar. Does that make sense? You can go through dimensional analysis if it helps you to do that. That's always a great idea. I often still do that myself. Okay, so this is just multiplying this out. Jerkily enough, I asked you to have this in years, and this is going to spit out in seconds, right? So all you got to do is just go through your dimensional analysis to get yourself from seconds into years. Does this make sense? These kind of half-life equations are things you're going to want to know how to do, and it's just going to be a matter of really just figuring out, do I have a first order or do I have a second order? And that will help you figure out what equation you need. Okay. This one, yeah, we could go over this one. I don't want you, I don't think we need to spend a ton of time here, but this one looks a little bit difficult because it seems like we don't have enough information. But the catch is, and before I launch into this, any questions for me about other topics, anything at all? We still have a good amount of time here. I really want to hear from you all about concepts that don't make sense. Yeah, so the question is, why isn't this second order? Isn't it the same reactant? Yeah, so it feels like that, right? But it is, in this reaction, these two things have to come together in order for catalysis to happen. So it's not just one thing is hanging out there and it turns into the product. These two things have to come together. It's just that these two things happen to be the same thing, right? So I can't tell if I'm in the slide because I'm in presentation mode, but right, this actually isn't good because they aren't the same thing. But anyway, it is second order because you have two things coming together. It doesn't matter if they're a different thing. It doesn't matter if they're the same thing. It is still a second order reaction. Okay, can you do an example? Yeah, great. Yeah, exactly. Okay, Michaelis-Menten equation. Let me see. That's a great one. That's better to do than this. Okay, so I don't see one, but we need to do that because it's important. Let me look actually real fast. I bet you we have one. I bet you we have one in our back of the chapter questions. So let me pull that out real fast. Or you know what? I can just make one up right here and now. Let's do this. Okay, so I'm going to put in a new slide. Okay, and so if we have questions that come up as we were studying, should we save them for office hours? Can we also reach you through email? Office hours is super ideal. There are, just shy of 200 of you and one of me. So emails, I tend to kind of deal with them all in one big glump. So it means I get to them a little bit later. So I always prefer office hours just because I can deal with them a little bit better. I will answer emails. I just may be a little slow because it can get a little overwhelming if everyone emails, but I will answer emails. Okay, so let's do this. So I'm gonna grab this equation so we can keep it handy. That will be a lot easier. Okay, so I'm gonna pop this in here. And let's just make up some things. So let's say, for example, when enzyme, because we all love this way of wording things, when enzyme is fully saturated with substrate, the observed, the rate is 72 per second. Okay, the Km equals, I don't know, 19 micromolar. What is the K-obs at substrate concentration equals 15 millimolar, or let's do this, 0.1 millimolar. Okay, so I've just made up something here. I think I have a calculator handy somewhere. So I need a helper to roll with me on this. But here's a made up question here. Okay, so what have I done here? Well, I've told you, and I'm gonna do this in a separate thing. Can you see this all okay? Is our happy faces in the way? Let me know if the positioning is not ideal. Okay, so what we're gonna do here is I'm gonna make a little answer box in here. And so what am I talking about when I say enzyme is fully saturated with S? Remember, those are magic words for something. And those are magic words for either Vmax or Kcat. And in this case, I gave you a rate, so that's gonna be Kcat. So I'm just gonna write here, Kcat equals 72 per second, right? That's gonna be a little cue to myself that I know what's going on. And I'm gonna get really grumpy that I capitalized the K. Okay. Little pet peeves for me. Okay, so let's start plugging this into the equation. It's not super terrible. Okay, so I have whatever my K-obs equals. That's what I'm looking for here. Again, super annoying. Thank you, Microsoft Word, for thinking your big old fancy pants. So I got 72 per second. And I'm going to multiply that by the substrate concentration. But hold up, troopers. I got to make sure that my substrate concentrations agree, right? And do they agree? No, they do not. I'm going to put this in micromolar, so I'm going to do 19 micromolar here, right? And then this whole shebang is going to be over the Km, so that's 19 micromolar. Wait, what? Wait, what? Nuh-uh. That's not my 19 micromolar up here. Whoa, whoa, gang. Okay, that's going to be 100 micromolar, right? So I'm going to convert this 0.1 millimolar into micromolar. So that's why I get 100 micromolar here. That's the substrate concentration. And so I'm going to add, make this longer, I'm going to add 19 micromolar, which is the Km, right, to 100 micromolar, which is the substrate concentration. Okay, so look out. I'm going to do some math. And let's see, we got 72 times 100. And that's 7200. What's our units there? Micromolar per second, right? Okay, not so bad. What else do we have going on here? Now we got to add together 19 and 100, and I am a master of mental math, so even I can handle that one. So I'm just going to divide 7,200 divided by 119. And what does that give me? That gives me 50.5 per second, right? And if I think about sig figs, which I, sadly, unfortunately, kind of have to, I technically probably would just call this 50. I'm going to make things a little easier. Going to give me 0 here. So at least I can report this as 51 per second. Did anyone do this along with me? And anyone want to veto my math on this? That's what happens whenever you're mathing up a storm in real time. So if anyone has any math comments for me, you can go nuts, but I think that might be okay. So does that help for Laura that wanted an example using the Michaelis-Menten equation? You're just going to be variations on a theme. You're either going to be solving for equation problem. Oops. You're just going to be solving for one of these different variables. You got 60.5. See, that's why I like that we do this together, because I get nervous sometimes. Okay, so let's do this real fast. So we got 72 times 1, 2, 3, 100, so 0.1 times 1,000, so that's 100 here. And then we got 19 plus 100, so I got 72 times 100. That should give me 7,200, and I'm going to type in 19 plus 100 because maybe I screwed that up. Okay, so 72,000 divided by 119 is, yes, thank you very much. See, I knew I couldn't trust myself to do math in front of an audience, a studio audience. See, you always think your professor's all fancy and smart, and then they just get scared when they have to do math in front of people, just like you. Okay, so yes. I agree with you. Thank you, team. Where would I be without you? Okay, so I wanted to word this a little bit differently, just to show you the different ways that I could do this. I could also, another way to say this is, the kcat equals 72 per second. The km equals 19 micromolar. And what is the k-obs at substrate concentration equals 0.10 millimolar. And alternatively, I could say, what is the rate? Let me just scroll this up. What is the rate when substrate concentration equals that? So let me show you this too. This is another way to answer the questions. You just got to think through of what I'm actually asking you here. So I'm going to emphasize that both of these ways are ways to do this. Okay. Okay, so this should get at your question here. So I could ask you, when enzyme is fully saturated with S, I'm going to highlight this and say code for kcat, right? So if you see me talking about, or Vmax, depending on what I'm talking about. Okay, so when I say enzyme is fully saturated with S, the rate I'm going to tell you about is either going to be a kcat if it's a rate, or Vmax if it's a velocity. Okay, and so I'm telling you that's that. And then I give you these other parameters I'm asking you for k-obs. I could also call this, what is the rate at substrate concentration of this, right? So I could say, what is the rate when substrate concentration equals that? Or I could say, what is the k-obs, right? Same thing here. And I showed you that kind of variation here where I'm saying the kcat equals 72 per second, the km equals 19 micromolar. And what is the rate when substrate equals this? What is the rate can be ambiguous depending on how I'm defining it. It could mean k-obs, it could mean kcat. I know it's going to be k-obs here because I've already defined kcat, right? But these are both ways to ask this question. If you got confused on an exam, feel free to ask it. I may not answer this one as much because I would want you to kind of scroll through your clues and figure that out. But fully saturated means that I'm telling you the kcat. So yeah, you're probably solving for a k-obs or a substrate concentration or a km, something like that. Does that help on that? Okay, and actually it looks like we're down to a minute, so I just wanted to take this last minute just to say this real fast. I've really enjoyed having and meeting and knowing you all this semester. And I can't tell you how grateful I am that you were my quarantine class. You all are kind people. You're very patient. And understanding that these are difficult times for everybody. So I really appreciate how kind and gracious that you've been as we've all been navigating the changes this semester. I also wanted to emphasize, you know, if you're here right now, or if you're watching this later, or you're looking at these slides later, you are amazing. You should really celebrate yourself, because it's really hard to keep your educational goals rolling in these really difficult times. If you aren't watching this right now, and you aren't watching it later, and you aren't looking at these slides, show yourself some kindness too, right? So tell your colleagues that might fall in this category, because it also takes strength and courage to assess what you need to do to keep yourself and your family safe. And I hope you have looked at credit and no credit options in this scenario. But everybody here, everybody not here, has things to be really proud of this semester. It's been an utter pleasure working with all of you. I'm really excited for you taking these next steps in your scientific careers. You all are so bright and interesting and wonderful people, and it's been really neat. Don't forget to come to exam 3. If you've been watching this class asynchronously, you do need to actually take it during that time. If you have something that prevents you from doing this, you need to tell me as soon as possible so we can work out an alternate time. Please do. We should still be doing course evals this semester. Please go ahead and carry on with that and write an eval on web portal. That's where I'm going to be posting your grade. So while you're there, check out your grade. I'll probably put that information on Blackboard a little bit later, but it will also be on web portal. Your memes are going to be due, I think it's on the 11th. So on the 12th, I have in my calendar to go ahead and put those things up. But anyway, thank you so much, all of you. I wish you all the best. Please take good care of yourselves. And I'm really excited for better times in the fall. Rest up this summer, take good care of yourselves, study up. I'll see you in office hours. And that's it for me. Thank you. And thank you all for these kind comments.